Everyone's read the title, so I'm not going to read it again. So it's a tradition in pipeline, especially when we do long talks, to have a safety moment. So bear with me and my poor acting for about 2 minutes.
Oh, yeah. Ooh. Hey, you're disturbing me. I'm reading Jim Oswald's new book. Pipeline meetings always start with a safety moment, so we'll do that today. As engineers and geoscientists, we're more likely to be interested in things rather than people, which will be an important point later in the safety moment. One of the indications that you may be interested in things over people is the fact that you've got a nice big garage, but both of your cars are in the driveway in the middle of winter. If I'm a bad guy, all I have to do is smash your window, reach into your car, and either use your panel-mounted garage door opener, which is programmed, and or I think someone might be getting a few fixes off of what's in here, even in a quick smash and grab. Let's consider too that most people don't lock their doors within their garage, and a lot of people tend to leave critical stuff right in their entryway. Hey, look at this! Ooh!
So my recommendations are, if you use a normal conventional garage door opener, either keep it with your keychain and or hide it in your vehicle in a place that a thief is not going to find during a smash and grab. Alternatively, if you're using one of the vehicle self-learning programmable garage remotes, make sure that it only operates when your key is in the ignition. Alternatively, I can suggest using a phone-based app that, of course, no thief will have access to.
I hope you found that more interesting than the slip, trips, or falls or ladder safety. So I've got to give you the obligatory outline for this, which I'll give you some opening remarks, a little bit of 101. We'll talk about ground and pipe monitoring as I see it. And then I'm going to actually justify the title of this darn presentation. And then we're going to give a little bit of a closing where I ramble on. And then, of course, we're going to have the grill the engineer question period. So there's been dramatic changes over time with geotechnical engineering. And I'm pretty lucky where it's happened over my career, I feel, because now we're harnessing the power of lasers, computing, satellites. And of course, we can beam information all around and over the place now, so we may not even have to go to site. Okay, so today's story starts back in 1956, when an engineer, Doc Hardy, was putting in a right-of-way for a new pipeline in British Columbia. Now, back in the day, we did not have the understanding of landslides that we do nowadays. And particularly with new technologies, what we can see is amazing. We can actually see through the trees now. So if you look at this, I'm sure if Doc Hardy had this information back in the day, this pipeline would have been routed around this deep-seated landslide. Just for reference, this is a couple kilometers long and a couple of kilometers wide. Just to let you know, Doc Hardy's real name is R.M. Hardy. There might be an award or something. Apparently, he's slightly prestigious. So let's go to 2019 now. And I found it quite interesting where I'm out on a site with what I consider to be a very excellent engineer I work with, who's younger than me, as most people are nowadays. And he looked at me and said, "How did you do it back in the day?" And, you know, my reply to him is, we did a lot of walking and a lot of geotechnical theorization on landforms. Okay, now let's go to today. And, you know, we even have differential LiDAR, and, you know, rather than even looking at the cumulative, we can just stack a bunch of GIFs on top of each other to figure out what things are doing. This is great, by the way, for VPs. to get action. Of course, we're interested in pipelines in this area right here, and I might talk about this a little later in the presentation. So what's happened over time is we've shifted from a focus on, do we have a landslide and what type it is, to what is the state of activity of the landslide, of course, using Cruden and Barnes 1996. So, and then the question is it active or is it inactive? And if it is active, we're concerned about how fast it's moving, and for pipelines, you know, cumulative displacement over time, over the life of the pipeline. So I put activity state in a different sort of description here for those that are not geotechs, where on the left panel, we describe inactive, dormant. And obviously in the middle panel, we describe active, extremely rapid. Okay, so as part of the big picture for this, I've come up with a soil to pipe landslide interaction classification system. And, you know, you can read this, but the main elements of it is do you have a non-interacting, exposing, or interacting landslide? And further to that, the main theme of this is whether these are maintenance issues or fitness for service issues. Now, I'll point something out in the system is I put exposing in. That is in there because of regulatory requirements and regulatory compliance. Some exposed pipes may be a fitness for service issues, where others are a maintenance issue. And of course, within any system like this, you want to predict the future state of this landslide and its interactions with your pipeline as part of your geohazard management program. So I'm going to give you 3 examples. 1, 2, 3, just to kind of warm you up a bit. So in the first one, we have a non-interacting earth flow, you know, residual soils in the Appalachians, where the landslide does not intersect with the pipeline, the slip surfaces above it, likely a maintenance issue. Then we go on to this, which I call in my system an eye impact. We had a rock topple, which you can see the before and after photo here, left before, center panel after, where we've got deposition of a rock topple, which breaks up and hits a pipeline right away. Now, there's a little quiz for later. So if anyone in the comments knows how we would assess the fitness or service of this, just put it in the comments to see if you get it right. Okay, and then of course we've got, I call it an eye debris, or it's also called an I.P.A, or an interacting pipeline Armageddon event. And so what you've got here is a rock slide up high in a mountain, which is turned into a debris flow, which come down and has ruptured. I think it's either a 12 or 16-inch natural gas main line. And you can actually see the explosion that resulted from this and the damage to the forest. And for scale, this is only a 12-inch or 12 or 16-inch line. There's 2 very large excavators. Now, let's switch now to the focus, which is velocity. So, you know, really for landslides, it's the extremely slow landslides, the R.E. Hardy example, or very slow landslides that we typically find pipelines in. And pipelines, you know, duration based on velocity can survive in these landslides for a certain amount of time. But for a conventionally buried pipeline, typically they'll only last for any time in an extremely slow moving landslide. And I think there's going to be some work done on this in the future by an engineer named Mike Porter of BGC, who's done some great work on this and goes into much more detail. I think hopefully it'll be at IPC this year. Now, if we look at pipeline features, this is just for the non-pipeline people. It's pretty simple. Pipelines are made by having a flat plate of steel, which is then formed, and it's welded along the long seam. And then when it gets into the field, it's welded, and those are the girth welds. Now, for those that are pipeline folks, I should mention slope inclinometers too. Kind of similar, where you have a plastic pipe and typically a 10-foot joint. And then there's probably 1 billion different types of commercial connections for these. And you put a probe in it, and you're basically profiling it using angles. Okay, so don't worry for the geotechs. I'm not going to really tell you what you already know, but I'm just going to give you my opinion on traditional geotechnical ground monitoring. So obviously there's visual monitoring, there's subsurface technologies, mainly slope inclinometers, which I'm going to talk about quite a bit today, and surficial technologies, which are conventional or GPS surveys, LiDAR, and INSAR. So for those non-geotech folks, geotech show up at one of your pipeline slopes, and they can do some visual monitoring and walk around and look at the pipeline. Often they'll recommend putting in slope inclinometers to characterize the movement, and particularly the depth of the movement, and they get indications of the rate of the movement from the slope inclinometer. And then what a lot of geotechs will do is put in surface survey monuments to give you more coverage on discrete areas of movement. And then with the new technologies, we can scan an entire area with either LiDAR or INSAR to give us ideas of rates of movement over the broader thing and give us more indications of the slide activity over a larger area. Okay, just advice to all geotechs. Nothing gets a VP's interest more than the photo of a split tree at a landslide scarp, okay? Now, typical visual monitoring, put stakes down or whatever and monitor rates of movement. We've all done it and we'll all continue to do it. But now let's look at surface survey. And if you look on the panel on the left of LiDAR, you look on the right, that's actually the surface survey of it, and it's providing very reliable results. Here's an example of, in a large landslide complex, I think it was that RM Hardy one I was talking about before, is you have clearly drift in GPS monitoring points to your right panel, and your left panel is indications of clear movement. And here we got up to 620 millimeters of movement, with an average rate of about 2 inches a year, let's say. So now the technology's evolved to the point where we can actually put GPS survey monitoring hubs real time, for pipeline applications. And those arrows on the panel to the left show real-time monitoring areas. And this is a surface pipeline segment that was part of immediate risk control measures as there was a landslide interacting with a pipeline. And this is a temporary measure waiting for an HCD to happen. If you look over to the panel to your right, what you actually see is the GPS survey monitoring hubs, near real time, monitoring the structure and the pipeline. Oh, don't want to do that. Okay, so now I want to make a point about surveying to the geotechnical audience. I think there might be a little bit of surface survey hesitancy amongst some very senior geotechs or amongst us all, because I don't know a geotechnical engineer over the age of, let's say, 45 that hasn't been burnt by a surface survey type monitoring installation in the past. But I want to put it in a pipeline context for you. And basically, your strain capacity of your pipeline, based on my experience, is going to be an absolute minimum 1 to 3 diameters of movement of your pipeline when buried in soil. Okay, let's talk survey accuracies. Whether it's traditional, GPS, or compound, which means that you have to use traditional and GPS together because you can't get the horizon for your satellites to completely go GPS because of trees, etc. And GPS real time. Worst case is you're going to get an accuracy of plus or minus 2 inches. Now remember the strain capacity of the pipelines. Okay, and just to sum up the monitoring. Okay, so this is an example of INSAR, and it's working perfectly. Your line of sight is perfect, and you're monitoring a deep-seated landslide. And the taupe circles on here are the surface monitor, the survey monitoring pins. Now look, there's the coverage you get from a slope inclinometer. And my point is, at this point, the slip surface is 100 meters deep, and it's a single slip surface. The surface survey pin is a 3/4 inch sucker rod, 6 feet long, hammered in by some gorilla, not me. And it goes from 0 to 1 meter. The pipeline's buried at 1 meter. So what's closer to the interaction, the SI or the monitoring pin? Now, let's switch gears to pipeline. There's been rapid changes in pipeline over the years. And a lot of it has to do with magnetism. And there's, the first main tool that came in, let's call it the magnetic flux leakage tool, which allows, it's not part of this talk, but it allows you to scan the steel of the pipeline to determine its thickness for corrosion and limited application depths. Then what's happened over time is we've got a newer, younger form of interpretation of magnetism, which has allowed us to develop axial strain tools, which I'll talk about. Then, of course, this all feeds into the state of practice today with smart pigs. And of course, computing power. And finally, what I'm focusing on in a lot of my research and work is cruise missile technology, or the LN-200, which we incorporate into pigs. So one of the things I want to mention, and I've known in industry, and it particularly happens the smaller the pipeline operator, is that pipeline and geotech tend to be siloed. And I'm going to provide some visual evidence of that right here.
You're pathetic!
That's my boy losing the race, by the way. Okay, so when we're looking at pipe monitoring, there's three basic subtypes of this. When you can do it from the surface, either through locates or electromagnetic tomography. The next is when you dig the pipeline up and attach something to it or measure something. And that's strain gauges, fiber optic cables, or axial strain surface probes, okay? Next is what I focus on, which is ILI tools, which is caliper tools, internal measurement units, or IMU, and axial strain tools. So let's go to the simplest. Sometimes technology does not have to be fancy. Here's the original pipeline alignment, and this is the new alignment. You could see the survey pins before I put the annotation over them and the landslide moving across it. Next is electromagnetic tomography, which is a blatant thing finder, but when you're using a whole bunch of technologies, it's a relatively cheap way to kind of give yourself a second check. And what you're essentially doing is, if you look at the bottom panel, is you're looking at the electromagnetic signature emitted by the pipeline. And where it drifts, that is indications of where you may have an interacting anomaly feature on a pipeline, or a feature of high strain and or compression. And there's a paper by Babcock, and basically 2/3 of all electro or bending strain features, which I'll talk about in a bit, correlate with pipe wall assessment features. I should mention too, there's no correlation between the magnitude of pipe wall assessment features and bending strains. Okay, next is strain gauges. These are something you put site specific on a pipe once you dig it up. And these are vibrating wires. There's various technologies for them, but they typically are around 2 inches long, and you have to have some expertise in locating them. And they're typically put at either 12, 3, 6, and 9 across a pipe, or at 12, 4, and 8 o'clock positions across a pipe. And here's an example of a photo of a welded installation. That's done by me, of course. And one of the advantages of this technology is that any painfully average engineer can implement this, as evidenced by my 2016 paper on this. So I've looked at probably hundreds and hundreds of interacting landslide data on strain gauges, or individual, let's call them installs. And the data completely makes sense and is completely reliable. The main issue with it, though, is when you put the strain gauges on, that's the starting point. You don't know where you're at when you start monitoring as far as the stresses and strains in the pipeline. So it's a useful tool, but it's got to be used very carefully. Now, here's an example of a pipeline being deformed, and you can see up here there's compression and tension in the upper left panel. And this is the results are shown in the lower left panel, and it makes sense. The neutral axis is at 12 o'clock where it should be, tension's at 4, and compression is at 8 o'clock. Everything makes sense. Okay, now this technology can be augmented if we use structural fiber optic cables. The advantages of these is you pretty much get near continuous strain data on a pipeline when you set up structural fibers at whatever position you assign to them, and you can interrogate them over large distances. You know, specifically, I think for normal fiber optic installations from a point in, you can interrogate it 20 kilometers upstream and down. It may be less for discrete like fiber optic strain gauges, but the point is, like I showed you a 4 kilometer long landslide. The longest pipeline I've ever seen in a landslide is, I think, around 4.5 kilometer long section. So this technology can be worked, but we need more research about this, and I find this very promising because opposed to strain gauges, you don't have to use any judgment when picking where you install them. Now, the final in-ditch technology I'll highlight to you, and I won't get into too much detail here because I'll discuss it in the Axial Strain tool, is that you use what's called the Valeria Effect, which basically is electromagnetic permeability. So it's pretty simple. If a pipe's in tension, your electromagnetic permeability increases. If a pipe's in compression, it decreases. And then what you do is you bench test, let's say a pipe sample in a 3-point loading to get the strains, and you can correlate it so you can actually determine the state of strain in a pipeline at each measurement area. Okay, now here's my favorite part of this, is the ILI IMU and the internal stuff, which is what I've focused a lot of my learnings on over the last 10 years of my career, which is caliper tools, IMUs, and axial strain. And I'll mention with ILI IMUs is that you can do an initial run, kind of like your initial run on an SI, and then you do run to run and compare it, just like an SI. So here we can see a wrinkle detected by a caliper tool. Here we can see that rock fall earlier that I showed you, which was assessed for fitness for service using a caliper tool. The before rockfall panel in the lower right shows the signature before the rockfall, and then you can see it after the rockfall, and it induced 3% ovality into the pipeline. The good news is you start getting nervous and start assessing things at approximately 6% ovality. This pipe was essentially saved by the fact that it was buried in a blasted bedrock trench quite deep. Okay, now, if there's one thing I'm going to teach you in this talk, or you should be concerned about, it's wrinkles. It is basically the last gas of the pipeline before a loss of containment in a landslide. And the example here we have is taken from a report on the 1610 landslide, which everyone can research on the internet. And we have a wrinkle forming at an overbend where an HED enters the ground in an active translational, I believe, landslide. The wrinkle is right in the center of the panel. Now, I will reiterate, if you have pipeline, wrinkle, landslide in the same sentence or conversation, you need to do an immediate assessment, period. And also you need to consider taking immediate risk control measures based on the results of that assessment. Now, let's look at the fundamentals, and it's real simple about ILI, IMU, or pipe shape determination. Pipeline girth welds are welded flush on straight segments of pipeline. If you look in the image, you'll see a bending machine to your far right, and in the center, you'll see a forged bend from a factory or a hot bend. And typically the signature, or what you do is you leave 2 meters of straight section at the end of the bend. And if you see bends across a weld, obviously something's going on. So I'm not going to get into the mathematics of all of this for everyone's sake, it's lunch, but I don't have to because Hart et al. In 2019 does a wonderful job of explaining everything you need to know about ILI, IMU data and how it's derived. But typically what we're getting is the pitch, the azimuth, and the odometer reading on a pipeline. And then of course, this is a function of the roll in the pipeline, and they correct for it. And then what you can calculate is the curvature of the pipeline from this data, which is commonly referred to as strain. Then if I show you a typical display of output we have from our software, is what you're looking at is a plan view elevation, horizontal strain, vertical strain, total strain. You know, remember, strain can also be considered curvature, and the azimuth and pitch. And particularly in areas like, I mean, I'd say like, for instance, applications in the Appalachians or anywhere where you're concerned more about horizontal movement across a pipeline, you can also do an out of straightness plot, which is a very good indicative tool to tell you may have an issue. So in my attempts to further advance this, in 2020, I proposed an ILI-IMU classification system, which I'm further revising right now through learnings and collaborations with other industry. Well, I'm not one, but you know, SMEs in the industry. And you know, it's based on feature source, feature type, and feature activity. And the one thing I'll point out to you is that regardless of the analysis you do, the majority of features you find are due to ILI features, which means some sort of reaction of the pig to a feature in the pipeline, like a proud girth weld, a wall thickness change, or a really tight curve, or due to maintenance activities such as integrity days. And that most of these features tend to be inactive over multiple runs. Now, let's go back to the founding of ILI-IMU analysis, and that was in 2004. So the technology's been around for a while in the pioneer papering by Sis and McClarty. And at a site called Daniels Creek, they noticed pipeline movement in a run-to-run analysis which was 1.5 meters. And then when they looked at the pipe shape, they determined that this 36-inch pipe had experienced at a landslide flank 4 meters of displacement over approximately, let's say, 50 to 60 years. And just to let you know what they did as part of this, and McClarty and Cavers are sort of a pioneer of this. It's not referenced in here, but is putting in surface pipeline segments so that the pipe is basically surfing on top of the movement on wooden skids. So let's look at another example where we have a landslide. And initially, you know, it's interesting because it's where geotechs have to talk to the pipeline vendors more. This movement was not initially detected because it didn't meet the criteria of the bending strain analysis the ILI vendor did. But when we looked at it visually and explained the landslide mechanics to the ILI vendor, they quickly pointed out to us that over 17 meters, we had 1.8 meters of displacement on the flank of the slide. And I'll tell you in subsequent analysis, this movement was picked up. So what I want to point out here, and somehow the automatic is taken over, so forgive me on this, is we've got a 30-inch pipeline on the right of the image and a 12-inch on the left. And you'll notice, of course, that pipeline stiffness has a significant component when you're factoring out your soil-to-pipe interactions. The bends are much tighter on the 12-inch. So when I classify this feature in my system, it's a horizontal S-bend, active uniform rate of growth in the feature based on 4 runs, and it's a landslide, translational, perpendicular to the pipe axis. And according to my landslide classification system for soil to pipe interaction, oh man, you gotta love Microsoft. Let me go back here, or the operator. That is what we're looking at right there on the flank of a landslide. So let's go to a more complex example now, where we have a pipe which has been strain relieved multiple times in a valley where one side of it, if you look at the panel to the upper right, on the northwest side is moving, and the northeast side is not. So we do strain relief on the northwest side. And we're going to look at this area in more detail on the future slides. So I don't even need to do any plotting to tell that there's an issue here or that there's deformation of the pipes. So if you look down at the pitch of the pipeline, and trying to see here if I can put the laser pointer on for this. Okay. Normal bends have a uniform rate of curvature. So if you picture the pig changing pitch, it does it at a uniform rate. So you end up with, which is what called ramp functions that define your bends in the field. And you can see that over here on these smaller field bends. And then in here, it's almost like these ramps have been melted. And that gives you an indication that the curvature is not constant on the bends, which indicates some sort of interaction. Now that pitch is in the vertical direction, just to let everyone know. Now, if we go up here to the azimuth on this too, we can see that horizontally, pipelines are typically put in straight. This is not straight. So there's changes also in the azimuth if you look at the plots. Now, let me turn off this tool. I wish there was a quick way to do that. Okay. And go to the next panel where we actually look at the curvatures on the pipe. And one of the diagnostic features is, if I look at, if you can see my cursor here, it is the lower right triangle. You can see that there's a weld with a bend right across it. That was not installed in the field that way, or I hope to goodness it wasn't. You know, put everything together, you have a landslide interaction. Now, let's look at this slide here. If you look at the panel to your left, you're going to see it's called yellow jacket coating, and where they've done the girth welds, it's wrapped, and those wrappings have been peeled off the girth welds due to landslide movement. And if you look to the panel to the right, if you can't notice the horizontal wiggle in that pipe, I just suggest leaving the meeting right now. It's okay. It's okay. This pipeline was also installed straight. So when we look at the ILI-IMU on this, the point I'll make is, and now we're not looking at the pitch so much as we're looking at the azimuth, which means the heading of the pig as it goes through this section of pipeline. And what you're going to see is the pipeline is slowly turning right and left as it goes through this landslide interaction. And this is clearly indicative of something's going on. According to my landslide classification features, it's a segment of compression, it's clearly active, and it's caused by, because we also did strain relief here, landslide and stress strain relief. It's a dual symbol for the source. And my final example is on a slope up near Fort McMurray, where it's a complex landslide sort of layout. We have three sort of types of landslides: superficial sort of flow / rotations in cluvium, then deeper seated translational type slides in cluvium, let's say up to 7 or 10 meters deep, where there are deeper pockets of cluvium. And then in this Cretaceous Clearwater formation below, which is a clay shale, you have deeper seated translational landslides. But we're concerned about the upper landslides here and how they're interacting with this pipeline. And just to let you know, for the terrain types that are on this, I certainly didn't bother delimiting every scarp on here, okay? Just to make that clear. So if we take a look at this, we can clearly see all the scarps in activity, and we're concerned about an upper zone, if you look at the panel to your left, and a lower zone. And if we look over at the actual plot, we can see the upper and lower zones, and it lights up like a Christmas tree when you look at the horizontal out of straightness in them, the bumps. And this is indicative of small, shallow flows horizontally deforming a pipeline. There's also, because it's going down to, you can see vertical deflections. And the classification of this is a W bend. It's clearly active, and it's clearly due to a landslide. I mean, there's no doubt. And I'll let you know here, in this case, the operator immediately went to risk control measures and installed a surface pipeline segment. And then, as time progressed, they put in an HGD to provide a permanent hazard avoidance mitigation option.
Right, or 25%.
I cannot describe to you how actually loud that was. You could see that I actually had a reflex reaction when that pipeline popped. Now, this pipeline obviously has no pressure or no product in it. And you heard me during that say 25%. What I meant by that was that when it tore apart, the cut around it was 75% through. So it sheared through 25% of the wall. Now, if you consider you bury that pipe and put pressure on it, that means that you're probably somewhere around 45% of any strain demand limit, I'll call it, or you know, something less than that in your ultimate strain capacity. But the point here is that ILI-IMU will not find this, because this is an area of gradual roping over a long distance of pipeline. I think in an Ottawa paper, I've defined this as an area of accumulated movement or cumulative movement or something. But ILI-IMU doesn't find this. Also, ILI-IMU, because there's little shape change, is if you have pure compression on a pipeline. It's not going to identify that either. So what do? Well, the key to that is a developing technology called the Axial Strain tool, which is a proven technology, but I would say that we're still developing the ultimate application of it. And so right now, it's basically 8 of those stress probes I showed you before, in a pig on arms that measure the state of strain in a pipeline. This is what your outputs look like. So you get a pipeline chainage in green, and then you get the actual strain results for, let's say in this case, 8 probes. And then you get their positions along the pipeline. Now the pipeline's rotating as it goes through the pig. So, the pig is rotating when it goes through the pipeline. So it's not quite as easy as what you think. So I'll make a comment too. If you look at this data, there's nothing happening on this data because like 90% SMYS in most pipelines can be pegged at somewhere around 2,700 microstrains. Now let's go on to look at what some of these results look like. So if you use an axial strain variation, which is what the vendor uses for the axial strain tool, it's essentially an average of the probe readings, and then they subtract out the tension, induced tension due to the pressure in the pipeline. You end up with sort of checking tensional and compressional trends along a pipeline. And that in that RM Hardy landslide, it actually shows it quite nicely that you have tensile and compressional trends within the pipeline. Now, one thing, the critics of this originally said something that, obviously on steep slopes, you're going to have a different signature. Well, if you can see, there's ground contour in the upper panel, you can see the steep slope it crosses and the signature remains relatively uniform. Now, if we go to the bottom, this is sort of the stuff I've been working on a bit, which is you actually go and do a structural analysis and plot the E-mins and E-maxes based on the probe data. And then if you actually have calibrated data, which is another topic, you can actually look at it in a context of fitness for service based on SMYS of the pipeline. So how does axial strain right now fit into the big picture? Well, that previous panel I showed you, I didn't give you all of it because what you do is you add an axial strain panel right at the bottom, which gives you your tensional and compressional results. Okay.
Do you know
That is now my universal, I'm going to shift directions and wrap this darn thing up slide. Also, it gives me a chance to take a drink. Okay. So I asked some industry SMEs to provide me with some awful SI, absolute position and or profiles. Okay. So what's this got to do with pipelines? So say I take these, I turn them around and turn them into a pipeline. Pretty similar, don't you agree? Then what I do, put a ground surface in a landslide and then some post-install deformation, and I think we got a pretty darn good analogy myself. Okay, so let's look at our little pig here and let's try to get some correlations going. So your azimuth and pitch typically will be equal to your A and B direction, just rotate it. And then the roll of the pig is equal to your spiral in your casing. Your probe length is 0.5 meters, may be similar to the actual pig length that the ILI-IMU is incorporated into. But where it changes is when you get into data collection. ILI-IMU, depending on the velocity of the pig, essentially the faster it's going, the more data you get. You can get data down to, let's say, 2 centimeter to 20 centimeter resolution. So I'm going to take a Dewar sidebar on this now. And so in SIs, essentially, we have a gauge length. And then what we're doing right now in geotechnical terms, if I superimpose how we read SIs, is we pull it up and we have the gauge length is also your sampling interval. So what we're doing essentially is measuring and summing angles. See where I'm going with this? So what can happen now is if that's the SI gauge length, we could actually change the pull gauge. I can see right now that a lot of interns and summer students and junior engineers are cringing. But of course, you'd only do this over the slip surface, and this is academic. And then you could also shorten the length of the pig. And what that would allow you to do is, rather than measuring angles, you could define curvatures in your SI casings. I just want to do this over slip surfaces, because my point is that, and maybe someone will correct me on the call of this, but our true understanding of what's going on when we can no longer pass a probe in an SI casing is fairly limited. We say they're sheared, but they could be blocked or they could be pinched, which I'll show right here. Now, the other thing is, as part of that, is if you're defining curvature, if you look at the final profile of an SI there, no matter how much measurement you do of curvature, you can never define a miter bend or a pure kink. So what you could then do is apply ILI IMU type caliper technology for small diameter pipelines to looking at these. And like I said, this is academic, but it's just an interest subject of mine where I don't think there's a lot understood about this. And if we're curious, there's an opportunity here. Now, I'm going to get to the vision statement and all that now. Okay, so right now, we have geohazard management, and we have some great tools for this, and we have some really good knowledgeable SMEs. We have ILI data analysis, which is partly what I'm talking about right now. And it's the integration of these, and then pipeline records and data, incorporating them. And I'll explain that in a second. And also, what I haven't mentioned in this talk is the rapid evolution, for instance, of these axial strain technologies and, like our pipeline, mechanical, structural type engineering, and incorporation of detailed, like discrete element analysis models. One day, I think, maybe in 20 years, we're going to have a complete scan tool, which is going to go through a pipeline and pretty much do your fitness for service assessment for you. Very little judgment required, other than, when the anomalous conditions occur. And of course, there's the smart computers that'll have to put this all together because our brains can't handle this. But people go, why are pipeline records and data so important? Well, that comes back to the fact that, like I said before, about construction and ILI-IMU features. And if you look at this, like I looked at 177 bending strain features as part of looking at the axial strain data for a paper. And I only found that 2% of the actual features were landslide related. Now, the mother of all studies was done by Terrio et al., where they looked at 4,600 features. And over 90% of them were construction related. Okay, so that says a lot right there. So company records are very important to help weed out the chaff, so to speak. Of course, there's smart computers that have to be involved in this too. Now, let me give you an example of this. We've got a pipeline segment which crosses, and there's two landslides on this slope. And there's an area with horizontal anomalies situated between the toe of one slide and the scarp of another interpreted slide. But I mean, if you look at the company records and you look at the image, it's pretty clear that this is a road crossing. So in a single run, the question is, are these strains due to a road crossing or soil to pipe landslide interaction? Well, in this case, I'm pretty sure they're due to the road crossing, because what happens is field crews like to tie things in. But if you had photos and records of the actual crossing construction, that would help you. Of course, the only way you concretely verify this is a run-to-run analysis to confirm that the feature is inactive, or if you monitor the landslide to confirm its activity. But then again, there's some nebulosity because maybe the landslide moved before and it's not moving now during your monitoring period. And of course, also, I'll mention to you, there's Dewar's chirpiness factor. This is unpublished. But what happens is the smaller diameter your line, the chirpier it gets, especially in the vertical direction due to installation. And unfortunately, when you get on a slope, you end up with more installation-related chirpiness, which sometimes makes single run interpretation very difficult. Okay, So let's talk about the future. What I'm going to see going forward is I think we're going to be doing less subsurface investigation with characterization as we bring this IME stuff on board and use it. I also think there's going to be further development in LiDAR and INSAR stuff. Pipe monitoring. There's going to be refinement of the axial strain tools, and we're going to go towards that one tool I talked about. And I hope, and I really hope I can be part of this, is further refinement of how we interpret IMU data and caliper data incorporated into geohazard management programs. And the sunny thing I want to say is mitigations. You know, over my career, the certainty of completing an HCD, and we can complete them longer now, is becoming better. So HCD, and I always recommend hazard avoidance rather than risk control by, you know, slope stabilization, surface pipeline segments, and that, is becoming more of an option at more locations. Now, before I wrap this up, I have to unfortunately do some blatant self-promotion. I have a plan. If it's in person, I'll have to think if it's virtual, because I think everyone knows how draining this is presenting virtually because there's no audience feedback. I plan to do a course at the Canadian Geotechnical Society this year on pipeline geotech. The premise of this is it's 8 o'clock in the morning, and everyone in the course is my legacy, and they're going to work for my company, and I'm going to die at 5 o'clock. That's it. And I'll talk about what we talk about today, and I'm also going to add in pipeline construction activities, you know, they did what, and discussion in more detail about how to do geotechnical mitigations. And of course, as part of that, we'll also discuss, amongst other things, emergencies, pipeline rules of thumb, strain relief, operations on steep slopes, and of course, how to violate hotel rules and not get caught. So I'm just going to go 1001, 1002, 1003. And the reason I'm doing that is so you can take a screenshot of these references later if you have any interest in some of these topics in more detail. And with that, I'm done.
Doug, you were just talking about taking screenshots, but actually, would you be willing to provide the slideshow as a PDF to the audience?
100%.
Awesome.
Yeah. And look, that was almost exactly 50 minutes. So at least I did something right today. So it's time to grill the middle-aged engineer.
Great. Thanks very much, Doug.